Yeah, it's great to be here, and it's great to talk to so many people, and especially for me, since my background is more extragalactic, to talk to a lot of galactic people. So, although I'm presenting something which is galactic, yeah, I'm still learning a lot more about this, and I hope I can add some spice to the discussion that we had already about HCN and how we trace dense gas. So Jens presented already the survey, and here in my talk, I want to talk about these three regions here that are part of the LEGO survey. And those are the three most massive star-forming regions. One of them was already presented yesterday in a talk by Frédéric Mott, W43. The other one is W49A, also very well-known star-forming region in the massive star-forming region in the Milky Way, and maybe a bit less known, G45, but there's also a lot of star formation happening there. So I will have three main science questions that I will discuss along the talk, which are all around the topic of understanding star formation, and in particular understanding dense gas and the concept of star formation. So when we want to understand dense gas, we have to infer it somehow from observations, and in this case from molecular line observations. And there's still a big debate how we can properly do this, especially in external galaxies where we don't have the same sensitivity that we have in the Milky Way to detect faint lines like N2H+. Then, taking that a step further, we want to understand these tracers better and how physical conditions drive these. So LEGO is a perfect survey to do this because we have all of the ancillary data to understand how these tracers correlate with the physical conditions of the gas. And then we also want to go back to the extragalactic regime and learn something. What are the most useful tools based on what we learn on the Milky Way that we can use extragalactically to understand gas conditions and star formation? So let me introduce the sample to you in a bit more detail. So these three massive star-forming regions are at a distance of about 6 to 11 kiloparsec, so relatively far away compared to Orion. This is, of course, a disadvantage in terms of resolving all of the great substructure, but it's an advantage when we want to compare it to extragalactic studies because we have large field of views here. And this is what we invested a lot of time with the ERM30 to really map large regions here. So you can see these fields of views are about 60 to 100 parsec across. So we're capturing the whole molecular cloud, not just the very dense clumps. And this makes this the perfect sample to compare with extragalactic studies, where we also typically have a beam which is at least as large as this whole field of view. So this is how the data looks like if we look at the spectra, for example. So you can clearly see we have clear detections of lots of molecular lines. This is only a selection of some bulk molecular gas tracers and some dense gas tracers. And now I want to take the extragalactic perspective here in my analysis. So the analysis that I'm showing in a second will just integrate over all of the emission that we see, because that's what we typically do extragalactically. We don't select individual components because we cannot resolve them often, at least at kiloparsec scales. So we have everything within the beam, and that's the same procedure that I will follow here. So all of these multiple components will just be summed up. All of the fine structure that we cannot resolve extragalactically, we just consider all of the emission. And then you can produce beautiful integrated intensity maps. And those are also coming with dust SED fitting to give us independent measurements of the column density of the gas that we can then convert from dust into gas surface densities and the dust temperature, so that we can study the emissivity of these lines in the dust temperature, dust column density regime. So let's first have a look at how these lines, or some of these lines, behave as a function of the column density that has been inferred from the dust. So we've seen these plots already by Mario and others. And here this looks quite similar. So we get relatively flat trends for the 12 CO because this CO has a low critical density. It eventually becomes optically thick and then freezes out. So we get relatively flat sublinear relations. Then for these more intermediate gas density tracers like C18O and HCN, the trends become a bit steeper, roughly linear, although we see already some strong variations between these clouds. So they are not as well behaved as these more local clouds that we saw before. And for N2H plus, we see much steeper trends. And also we see that the emission is only here really occurring in the very dense gas. So N2H plus seems to be the only real selective dense gas tracer in these clouds as well. So we can look now, a bit more detail how these lines behave as a function of column density when we look at the emissivity of these lines. So when I say emissivity, I mean here now the integrated intensity divided by the column density. And we can look at the N2H plus here, and what we see is, and I added here also Orion A from the LEGO sample, that N2H plus is really robustly peaking always at these high column densities of about something like 3, 4 times 10 to the 22 per square centimeter. While for HCN, we see sometimes it's tracing dense gas, but sometimes it's tracing more intermediate gas density, or sometimes even behaves as CO basically, so not tracing dense gas at all. So it's not really selective of the dense gas. And this is also quite consistent with what we find in more local clouds in the Milky Way. What I found interesting though is, and this is also consistent with, for example, what Mario showed, all of these alternative brighter dense gas tracers like HCO+, HNC, CN, CS, they behave all very similarly to HCN. So it seems that only N2H plus, and probably because of its chemistry, is very distinct from all of these other tracers. And all of these secondary effects, like secondary excitation mechanisms, behave quite similarly for all of these lines compared to N2H plus. We can also add a dimension here. So because we do not only have the column density that I have on the x-axis, but also the dust temperature, to investigate how these lines behave in this two-dimensional plane. So what you see in contours here now is how efficiently these lines emit as a function of column density and dust temperature. One thing you can directly see is that the parameter space that we sample in these three different clouds is quite different. So in W49A, you see that where the gas is relatively dense, it's also warmer, likely because of a lot of star formation going on, heating up the gas here. In W43, it's much more complex. We have different cores in the field of view, and the same for G45. But what you can see is that, N2H plus is peaking here usually at this high density gas range. And in W49, for example, mostly where it's relatively cold, even so not in the very hot dense gas. While HCN is a bit more shifted towards the higher temperatures here. And we looked a bit more detail into how HCN is actually affected by the dust temperature. So here I color-coded the same plot that I showed a few slides back, but now with the dust temperature as this color map here. And what you then see is that for HCN, we see a larger scatter here than for other tracers, and B, we see a gradient here that shows us that at higher dust temperature, the HCN emissivity is higher. This could be a sign that HCN the emissivity is affected by other effects, such as infrared pumping. I'm pretty sure that one of the next talks will be discussed in a bit more detail. But this shows us this HCN is not only driven by the column density, although that's the strongest effect, but that the temperature can have a secondary effect on the emissivity, which is stronger than for other tracers. However, we also see this for the CO here a little bit. So when we take the ratio between HCN and CO, which was shown already in many talks before, some of these effects will probably cancel out. And this is why this ratio can be a powerful tool. So now I want to put these clouds a bit more into the extragalactic context. So we've seen this relation already before, the HCN luminosity versus star formation rate tracer, and then also here the ratio, which we can refer to as the Gauss-Solomon relation. And now I'm putting these three clouds as integrated measurements. So we just integrate all of the luminosity within the field of view and take the star formation rate from an infrared measurement and put them on this relation. And what we see is they fit quite nicely onto the relation. They're a bit on the upper end, but not super much. So it seems while W43 was presented to be like way above the K, or at least significantly above the Kenniker-Schmidt relation, it's here quite consistent in terms of the HCN luminosity. And the same goes if we put them onto the scaling relations that Antonio showed this morning with the cloud surface density and the line width of the CO as a measure of the velocity dispersion. We see that they fit quite nicely onto our extragalactic scaling relations that we have from nearby star-forming galaxies. So there's two things we can take away from this. One is these molecular cloud regions seem to be quite consistent in their properties with our nearby star-forming galaxies that we study. And B is that these regions seem to be relatively normal or even under average in terms of their surface density and star formation compared to what we usually have extragalactically. So even though we pick the most extreme regions in the Milky Way here, at least outside of the center, we still have quite average regions compared to what we usually have extragalactically. So now I want to also comment on this HCN to CO line ratio as a tracer of gas density. So we've seen this plot already before, and we can also put the LEGO clouds on this trend, and we see it's actually quite consistent. So we see an increasing trend with this ratio with the average molecular gas surface density. And a student that I have supervised in Bonn, Sabrina Stäfer, she looked at this also in the context of several other studies and found a relatively consistent trend across all of these studies with some smaller offsets between these studies, which could also be caused by different methods, how to actually infer here the H2 column density. But in any case, we always find an increasing trend, which makes us believe that this ratio is a powerful tool to trace gas density from sub-parsec to kiloparsec scales. And just two more slides on what Sabrina here did. So she combined LEGO or compiled the data set from LEGO with what we have extragalactically. So this is SWAN, what Sophia already presented, and Almond, what Antonio showed. And then also including higher resolution data from more nearby clouds from the PropStar survey, where also Jaime was involved. And we looked at how HCN and N2H plus compared across all of these studies. And when you look at how these two lines compare, we see a roughly linear correlation. It might be slightly superlinear, but it's definitely more linear than what you see, for example, between HCN and CO. So there might be some connection between the gas emitting in HCN and the gas emitting in N2H plus. However, this correlation breaks down if you go to higher densities and smaller scales. So if you really resolve the clouds, you get a much larger N2H plus to HCN ratio. So this made us believe that there are kind of two regimes. One at the larger scales where you have a roughly fixed line ratio, and then at the smaller scales where this breaks down. And here we found this to be roughly at where this breaks down at 1 to 10 parsec scales. Although, of course, keep in mind there's also some scatter here at the larger scales. But at least on average, if you look at kiloparsec scale trends in galaxies, HCN might not be so bad in tracing the dense gas that you would trace with N2H+. I just want to add, of course, the caveat, this is only from this very bisample, very normal star-forming regions, so no very extreme regions. So don't extrapolate this to every environment. And I'm going to stop here with my summary slides and take questions.
Okay, time for questions. Second. Thank you. Very interesting. About the comparison between N2H plus and HCN lines, you talked about the correlation between integrated intensity, but did you check the correlation, eventual correlation between line widths and peak velocity peak of the lines? Because this is more, I think, more indicative that they trace similar gas.
Yeah, we didn't look at the line width versus peak. It's an interesting comment, something that we can check. I mean, not so sure how well this would work across all of these different scales. But thank you.
Maybe something to check.
Yeah.
Well, have you tried other molecules than HCN? Can you do the same exercise, for instance, with C18O? Because if it starts at large scale, it means that you start just by counting clouds or fraction of clouds in your beam. So then the relation should work with many more molecules.
Maybe, but I think there is a fundamental difference in what HCN and 12CO is tracing. So I think there is a deeper connection between the HCN emitting gas and the N2H plus compared to HCN and CO. Not so sure about the C18. Yeah. Okay. What's going back? I'm not so sure about C18O. That would be interesting to check. I think we have less data exogalactically on C18O than we have for HCN.
No, but just check that your interpretation is valid.
Yeah.
And that, because at some point when you see correlation at large scale, it means that you count objects in your pixel. And then you find the same number of objects, and then you get a correlation. That's my comment.
Nice talk, Lukas. I have one question related to your interpretation of your results in terms of HCN. I mean, and other lines as well, but I don't know that much about these clouds. But what I know from Orion B is that Orion B from one side to the other really changes its properties, because on one side is kind of really UV illuminated. That also impacts the emission of some of these lines. Have you maybe investigated, or do you have any information on how UV bright these sources are? Are they exposed to radiation from young stars, and how much? Do you have any estimate of that?
They are most likely, because there is a lot of active star formation. And you see this, of course, one signature is the dust temperature, right? Where you see the feedback from the stars. But there are no high ones. There are. Versus it's low. I think we're talking about LEGO now, right? Yeah. So there's definitely a lot of high mass star formation. I cannot give you a number of the UV field, but yeah.
Yeah, I'm just wondering, because we know from Orion B that this really changes some emission of some lines. For instance, CN is highly impacted, and it's really important to consider this effect. So yeah, thanks.
Yep.